Hi everybody, welcome to my video on source models in probabilistic seismic hazard assessment. Before I start, I want to give a shout out to Jack Baker and Kevin Frank, who have awesome YouTube videos on these topics. They're true experts, and everything I learned here, I learned from watching their videos. So in this video, we're going to start out talking about what is a probabilistic seismic hazard analysis. Then we're going to move into talking about geologic source models. So how do we develop magnitude frequency plots kind of from geologic considerations? And how do we develop those same plots from seismic catalogs? And then we're going to finish talking about how we can combine them in hybrid models. So first, why do we need seismic hazard assessments? They inform building codes in seismically active areas like California. Essentially, there's a great need to understand what is the likelihood that this area where I'm building a building is going to experience some specific magnitude of shaking or worse. What's the probability of that in a year or in 10 years? And that's really how we think about how strong and how we should build buildings. So the goal of a probabilistic seismic hazard analysis is to come up with what's called a seismic hazard curve. And this is the product of a lot of different steps that we're going to be learning about in a few different videos. But it essentially plots ground motion, in this case spectral acceleration at a period of 1 second, versus the annual rate of exceedance of that level of ground motion. So how many times per year do we expect to have an event that's going to be at or exceed some acceleration value? So what we see is that for large ground accelerations, very violent large earthquakes, those may happen, once every 10,000 years. For small events that don't have much ground acceleration, those may happen every few years. So this is what lets us think about how often we should expect the ground to shake in different ways. So to develop a PSHA, there's 4 main steps. First, we need to identify our sources. This can be specific faults that are likely to produce earthquakes when they slip, or it can be just areas where we know there's probably faults, but we don't know where they are. Maybe they're buried, and maybe no one studied it. So we can either consider source areas or specific faults. And then for either of those, we need to develop a recurrence relationship, or I'm going to call this a magnitude frequency plot. For any earthquake of any given magnitude, how often is it going to occur? Then we combine this with what are called ground motion models. So for any size earthquake, say a magnitude 3, of some distance from our location, what do we expect the peak ground acceleration to be? And we're going to have another video about this. And then we combine all of these things together, usually using what are called logic trees, to develop a single seismic hazard curve or a family of seismic hazard curves, which again show, kind of ground motion like spectral acceleration versus probability. So in this video, we're going to focus on 2 ways to estimate recurrence. So we're going to be focusing on this part, or maybe you could say these 2 parts, 1 and 2. One is a geological model, or a fault source model, or a background seismicity source model. So we'll first talk about the geologic source model. So any geologic source model begins with well-mapped faults. And here we have an example of faults that are mapped near Salt Lake City, Utah. This is the Wasatch Fault System. This is from the National Seismic Hazard Assessment. And red faults are known to be active. And so we've also mapped these West Valley faults, and then you can see in the cross section that the West Valley faults come down and kind of tee in to the same master fault as the Wasatch Fault Zone. So this illustrates a couple of open questions that occur all the time in this business. One is, how frequently should we expect each of these segments to rupture? That's one. And then another one is, do we expect them to rupture all together as one single event, or do we expect them to rupture separately? And so the question there really becomes, how are these faults connected at depth? Is this essentially all just one big fault as you go down into the Earth, such that all of these strands are going to go together at the same time? Is that how we should model it? Or should we model them each as breaking on their own in restricted events? And of course, that would produce smaller earthquakes. So those are some of the challenges we face when we're developing a geologic source model. So the way that we think about magnitude frequency for a geologic source model begins with very often a scaling relationship. So Wells and Coppersmith showed that if you know the rupture length of an earthquake, it scales very closely with the total moment magnitude. Likewise, the rupture length also scales or predicts the average displacement or the average slip during an earthquake. So the implication here is that if you can map out a fault, you know its length, you can make an educated guess of the total magnitude earthquake that it's going to produce. So what we can do then is we can take that estimated magnitude here and we can plug all that information into the moment magnitude equation. So here we estimated this from length. This is the shear modulus, which we're going to assume. And then we can take that length, multiply it by the seismogenic depth to get a total predicted rupture area. And we know all this stuff, and we can solve for the displacement, the average displacement or the average slip in a full rupture event. And so then once we know that kind of predicted slip in a rupture event, we can turn that into a frequency by dividing it by the slip rate, okay? And here we're going to do this, we're going to assume what's called a slip predictable characteristic earthquake cycle, such that if we're expecting 1 meter of slip per earthquake event, we can multiply that by a slip rate, say 0.01 meter per year slip rate, and get a total of 0.01 earthquakes per year. So we actually get that frequency. And essentially what we're assuming here is that once we build up a slip deficit of 1 meter, then the earthquake's going to occur and release that amount of slip. And if we know the slip rate, we can see that it takes essentially 100 years to build up that amount of slip. So where do we get the slip rate? One place we can get it is from geodesy, and this is essentially using GPS or INSAR to measure the slip rate along faults, the rates at which faults are slipping past each other in real time, right? So this is data that's collected over the last several decades. Another way we can do this is by geologic slip rates. This is the classical way to do it. You may have a fault, in this case it's a strike-slip fault, the San Andreas, that is offsetting some landform like a river. If you know the age of this river channel, you can actually convert this offset into a long-term slip rate. So that's essentially the simplest and perhaps most common version of developing a geologic source model. So we can see that some of the benefits are that it's based on real geologic data, which means you're maybe more likely to accurately predict source parameters, like what type of fault is it? What direction is the slip going to be in? Where is the hanging wall or footwall going to be? And also we can make some pretty intuitive predictions of maximum event sizes, like is the whole system going to go together or is only part of the system? You know, what's the worst case scenario if all of those segments of the Wasatch rupture together? The cons are that we need to know all this stuff. We need to know where are these faults, right? We may need to know their slip rate. So this requires a lot of detailed geologic study that simply hasn't been completed in many parts of the world. Of course, we also need to make a lot of assumptions about rupture length. Is it going to be a full rupture or a partial rupture? And then we make all those scaling assumptions. We're trying to convert that rupture length into a magnitude, into a slip distance, and there's a lot of assumptions built in there. So this brings us to the next type of source model. That's a seismicity-based source model. And this is a completely different approach. So what we're going to do here is start with a seismic catalog. So this is a bunch of earthquake events recorded over many years where we know their magnitude, we know their location, we know their depth. And what we can do is we can create what's called a Gutenberg-Richter plot, where we essentially just plot them all. Here's their magnitudes, and then here's the rate at which they're occurring. So this is the rate at which, a earthquake of magnitude 4 or larger occurs. And it turns out that when we plot this data, it follows a very predictable functional form, whether we're considering earthquakes on a single fault or over some region. And that form is given by this equation. The log of the rate of exceedance, lambda, equals A minus BM, where A is this upper intercept up here, and essentially gives us a sense of the earthquake rate, right? Large A values mean lots of earthquakes are happening. B is the slope of the line, and that really tells us kind of the distribution of earthquake events. A large B, a steep slope, means that we have relatively large amount of small earthquakes, basically up here. A shallower slope, like this, would tell us that we have relatively fewer small earthquakes. So you're going to see these Gutenberg-Richter parameters popping up all over the place. And it's also worth just noting, right, what's the predictive power of this? The predictive power of this is that if you want to know, well, how frequently are we going to have a magnitude 6 earthquake, you literally just read it right off the plot. So this has a built-in magnitude frequency relationship. However, this does require that we clean the earthquake catalog quite a bit. We need to harmonize, make sure that all the events are on the same magnitude scale, get rid of duplicates, make sure everything is scaled to the same depth scale. We need to decluster the earthquake catalog. We need to remove aftershocks from it. And ideally, we need to assign earthquakes to specific faults if we can. So link them to their sources. So I'm going to talk about these last 2 points briefly, declustering and an association to sources. So declustering is necessary because on locked fault systems, what tends to happen is we build up strain, then we have a big event, one big event, followed by many, many, many aftershocks. And you can see that here. This is cumulative earthquakes in the Bay Area. And in 1990, we had the Loma Prieta earthquake. It was one big event, but it had many hundreds of aftershocks, which actually created a noticeable impact on the statistics of magnitude frequency. So if we don't remove these aftershocks, then it really biases our catalog towards these kind of smaller aftershock events, when what we really want that catalog to be biased towards is towards the single large event, because that's the one that we really, really care about. So to decluster, we want to essentially remove aftershocks from the catalog, and we do that using what's called Omori's law. This was a relationship that was noticed many, many, many years ago, and it's this simple idea that if you have a big main shock, kind of at time 0 here, the rate of aftershocks decays in a predictable form with time. So what you can see is maybe in the first 12 hours or something, the aftershocks are going pretty steady, and then they start to taper off following this functional form. And so what we can do is essentially fit these parameters, K, C, and P, and then use that to identify kind of the expected rate of aftershocks after a big event like Loma Prieta, and remove them from the catalog so that it's not biasing our Gutenberg-Richter plot. Okay, so here's what that looks like. Here's a raw earthquake catalog, again in the Bay Area, and here is declustered, so we've removed all the aftershocks. You can see we've removed a lot of earthquakes. This is also a good figure to remind us that whenever possible, we'd like to link these earthquakes to specific fault sources. So be able to say, these earthquakes all occurred on this particular fault, these ones occurred on this fault. And then we can develop Gutenberg-Richter stats for the fault itself. However, this is not always possible. And if we can't do that, we tend to use what is called a zonal approach, where we might break an area into zones or regions that we think are seismotectonically similar. Okay, they're behaving in the same kind of tectonic way, same type of rock, same stress regime, same number of underlying faults. And then we extract an earthquake catalog for each zone, and we build up Gutenberg-Richter statistics for that particular zone. So this example is from the eastern and central US. This is a classic place where we have quite a few earthquakes, but we really don't know what faults they're occurring on. Many of them are at depth, they're not rupturing the surface. The faults are buried by sediment, we just don't know where they are. So we really have to, this is where the background seismicity approach comes in huge. We're not really worried about what exact fault is an earthquake occurring on. We're just using the Gutenberg-Richter relationship for the entire zone. So the pros and cons of the background seismicity approach. As I just said, the pros is that it works in regions with little geologic study, so poor mapping, no paleoseismic studies, or regions where we just don't know where the faults are. It can be applied to source faults or to regions, we just talked about that, and it has a built-in magnitude frequency distribution. By definition, that's what the Gutenberg-Richter plot is. It is a magnitude frequency distribution, which is what we were trying to get at anyway. The cons is that you need a lot of accurately located earthquakes, which means you need a long instrumental seismicity record, you need a lot of seismometers. Really only developed countries like the US and Japan tend to have these detailed seismic records of well-located earthquakes. Another one we're going to see in a second is that this does not always accurately extrapolate to large earthquakes, and it can sometimes be difficult to predict or assess a maximum earthquake size. And then finally, we may not know what we have as much info as we'd like on the earthquake source parameters. What type of fault was it? What was its strike and dip? What was its orientation? Which side is the hanging wall? Which side is the footwall? So we just may not know much about the fault, which can limit our ability to model the shaking. So let's transition then into the last part of this video, which is about hybrid models and maximum magnitudes. So a hybrid source model can combine the strengths of a seismicity-based and a geologic-based model. And again, it's just another magnitude versus frequency plot, but the medium magnitudes are defined by the Gutenberg-Richter relationship, by the earthquake catalog. But you can see that this does not predict well the largest earthquake events. And it may be that if we have a fault that we've been able to study with paleoseismology, trenching techniques, for example, we may know from the geologic record that this fault produces a magnitude 7.8 earthquake, every 500 years or every 800 years. And we feel pretty confident about that. So we want that to be included in our magnitude frequency diagram. So we'll kind of tweak that diagram to come out here and kind of deviate from the Gutenberg-Richter prediction. And that's called a hybrid source model. And then along those lines, even if we're not able to make a full hybrid model, it's very often the case that we might use a Gutenberg-Richter or a seismicity-based model, but we really would like to know, what is a reasonable guess at the maximum magnitude that could be produced in this region? And so we'll often take a stab at this using what's called the ergodic rule, which essentially means let's go look at what the largest earthquakes have been in comparable areas, comparable seismotectonic settings, and then apply that to our own area. So an example here is that eastern US and central US example again, right? I showed all those earthquakes, but we don't have a very long record. And so most likely we're missing the biggest possible earthquakes that could occur in Missouri or in South Carolina or in New York, right? There just hasn't, if that big earthquake only occurs every 10,000 years, it just simply hasn't occurred yet, but it's out there somewhere. So what we do is we go around the world and look in comparable settings. So these are cratons in stable continental regions, right? And we gather up all the large earthquakes that have occurred in stable craton continental regions and ask what's the distribution of those large earthquakes and what is the maximum that we've seen. So in this case, the maximum may be 7.8 or 7.6. And we may include that as a priori constraint on our models, especially in Bayesian statistical models. So to conclude, what have we talked about in this video? A PSHA requires 4 things. Requires sources or source areas, a recurrence info, so that's the magnitude frequency plot, and then also ground motion models and logic trees, which are going to be the subject of future videos. Geologic source models develop that magnitude frequency relationship by combining predicted, I should say, slip per event with a geodetic or geologic slip rate using kind of a slip predictable model. Seismicity-based source models develop magnitude frequency plots or Gutenberg-Richter plots just based on an earthquake catalog. Hybrid models may combine geologic evidence with seismicity-based models. And it's very often that we want to invoke a maximum earthquake size based on the ergodic rule. Thanks for listening. Bit.